Hello friends, so today we are going to solve the question from heat and thermodynamics. And these questions are from the year 2018. We are going to solve one question, and from 2019 we are going to solve 4 questions. In total we are going to solve 5 questions, and all these 5 questions are from advance. So the first question, it was asked in the year 2018, and it states that 1 mole of monoatomic ideal gas undergoes an adiabatic expansion in which its volume becomes 8 times its initial volume if the initial temperature of the gas is 100 Kelvin and the universal gas constant is 8. The decrease in its internal energy in joule is. So we have to find out the decrease in internal energy when there is a adiabatic expansion and the volume is said to be 8 times than the initial volume. So we start with our you can say the monoatomic ideal gas, and it is said to be given of our 1 mole. So we can write that for monoatomic ideal gas, the internal energy that is our U, it can be written as F upon 2 nRT, where F is a degree of freedom and for monoatomic it is 3. So this F is degrees of freedom, and for monoatomic its value is 3. Number of moles N is given as our 1, and therefore we can reformulate the equation that U will be equal to 3 upon 2 RT. Okay, and the process is said to be our you can say adiabatic. It is given to us, so we can say that our first law of thermodynamics, first law gives us that our delta U will be equal to Q minus W, and the process that is given is adiabatic. So we have our adiabatic process, and for this adiabatic process the value of Q is equal to 0. Therefore we can write that our this change in internal energy delta U will be equal to minus of W. Okay, so basically means that the work done by the gas during expansion is positive, so the internal energy decreases because delta U is negative. Okay, so we can say the work done by the gas during expansion is positive. So which means that this work done W is going to have a positive sign. And if W is going to have positive sign, therefore we can write that internal energy which is our delta U will be negative, or we can say it will be less than 0. And also for adiabatic process we can write the relationship between temperature and volume. So we can say for adiabatic process we can say that the temperature volume gamma minus 1 should be equal to constant, and this gamma is our adiabatic index. So we can say our gamma is equal to ratio of our C of P, C of V, and this ratio is our 5/3 for monoatomic. Gas. And we are given that the volume during expansion increases by a factor of 8, that is given to us. So we can see if we are having an initial volume, is suppose V of I, therefore we can say that our final volume is equal to V of F will be equal to 8 times V of I. And we can reformulate our this relationship between temperature and volume in terms of initial as well as final. Therefore we can write that T final V final gamma minus 1 will be equal to T initial V initial gamma minus 1, and we can substitute our V final as 8 times Vf. So we get T final will be equal to 8 times V initial gamma minus 1 is equal to T initial and V initial and gamma minus 1. So we can just rewrite this equation, and we are going to get this as our Tf 8 raised to power gamma minus 1 Vi gamma minus 1 is equal to Ti Vi gamma minus 1. So this Vi cancels out, and from here we substitute value of our gamma, that is our 5/3. So we get this as our Tf 8 raised to power, so this will be 5/3 minus 1, giving us 2/3 is equal to T of I. And now it is, we can write our T of F is equal to T of I, and this will be coming as 8th cube root. Cube root of 8 will be equal to 2, and 2 square is going to give us 4. So this will be our 4. And initial temperature is given us as 100 Kelvin. So 4 giving us 25 Kelvin. So this is our final temperature, that is our Tf. And we are supposed to find out our change in internal energy. So we can say that change in internal energy, which is our delta U, will be equal to UF minus UI. and we already know the general formula of our U, that is our 3/2 RT. So we can write the same formula in terms of initial temperature as well as final temperature. Therefore we get this delta of U is equal to 3/2 R T of F minus 3/2 R T of I. 3/2 R we can take as common. Let me substitute value of R also, and this value of R is said to be taken as 8. Final is our 25 and initial is our 100. So this 8 goes by 4, so we get this will be our delta U will be equal to 12 multiplied by 75 minus, that will be minus of 900 joules. Okay. So in terms of magnitude only, we can write this as our 900 joules. Okay. Obviously it is decrease in the internal energy, because here also we concluded that the energy is going to decrease. So we get this is equal to 900. Next question. It states that it was asked in the year 2019 advance, 1 mole of monatomic ideal gas goes through a thermodynamic cycle as shown in the volume versus temperature, that is VT diagram. The correct statement is or R. R is the gas constant. So we have to find out. Basically it is talking about the work done and what are the processes associated and the ratio of the heat transfer respectively for all the processes. Basic diagram is given to us, VT diagram, and from here we can say that the process start from our 1 goes to 2, then 3, and then come back to 4. Okay. So from our 4 to 1 the process is going to have a volume constant, and also from 2 to 3 it is also having our volume is constant, but for different value. Okay. Rest of things we are going to formulate or find out how the pressure is going to behave, because it is going to have a different value of temperature, and from between 1 and 3 they are the same temperature. Okay. So we are basically given 1 mole and the gas is our monatomic. Okay. So we can say that the number of moles is our 1, and for our monatomic we can say that our internal energy U will be equal to 3RT, or we can say our change internal energy will be equal to 3/2R and change in the temperature, that is delta T. And we also know the value of the specific heat for constant pressure and volume. So you can say our C of V is equal to our 3/2 times R, and our C of P is equal to 5/2 times R, and we have adiabatic index, that is gamma, which is the ratio of C of P and C of V is equal to 5/3. Okay. And so let us consider the processes one by one. Okay, so in this case one important thing is that this process is cyclic, starts from 1 and ends at 1. So we know that, let me write first law. First law gives us that our delta Q is equal to delta U plus W, and for W we can use the general formula integral of PdV, and for our this cyclic process you can say cyclic process, our delta U will be equal to 0. Okay. So we can say that our delta Q will be equal to our simple work done. Now let us identify the various processes that are associated with 1, 2, 3 and 2 we know, and 4 and 3 and 4. 4 and 1 process we also know. So let us start with from 1, and let us call this process identification. And first process is from 1 to 2, and it starts from V0 and goes up to V0 T0 and goes up to 2V0 2 T0. So it starts from V0 T0 and it goes up to twice V0 and twice T0. And we are going to find out the pressure. So we can say that our pressure at 1, let us call this as P1, will be equal to R T0 divided by V0. And pressure at 2, let us call this as a P2, will be equal to R twice T0 divided by twice V0. Here this 2 and 2 cancels out, so this comes as our R T0 and V0, which is same as our P1. So this is equal to P1. Therefore we can say that it means the pressure at 1 is equal to pressure at 2. So basically we can say it is a constant pressure. Constant pressure. And constant pressure, so which basically means isobaric. Okay. And if you look closely also, we can also see that the first is V0 T0 and second is twice V0 or T0, twice T0. So from here we can also write that V is directly proportional to T. Okay. So we can also say that V is directly proportional to T. And let's go to the next process, that is from 2 to 3. And 2 to 3 we are having twice V0, twice T0, and it goes to twice V0 and T0. So here we can clearly see that our volume is constant. So basically it is isochoric. So we can say that our volume is constant. So therefore isochoric. And let us find out the pressure. So at 2, let us call this pressure as P2, and that is equal to our R, and this comes as twice T0 divided by twice V0. So here this 2 and 2 cancels out, and this comes as our R T0 upon V0. And pressure at 3, let us call this P3, will be equal to R T0 divided by twice V0. And we can say our P3 is equal to P2 divided by 2. And let's come to our 3 to 4. And 3 to 4 we have this as twice V0 T naught, and it goes to our V naught and T naught divided by 2. So pressure at 3, that is our P3, is equal to R T naught twice V naught. Pressure at 4, that is P4, is equal to R T naught by 2, and this is our V naught. So this comes as our R T naught divided by twice V naught, which is nothing but our P3. So once again, the pressure at 3 is equal to pressure at 4. Therefore, we can write this is constant pressure. And we are going to have this as our isobaric. Okay. And let's come back to our 4 to 1. And we have this as V naught, T naught by 2, and this comes as V naught and T naught. So once again, volume is constant at V naught. So we can say that our volume is constant. So we are going to have this as well as isochoric. And we can easily find out the pressure. The pressure at 4, that is a P4, will be equal to R T naught by 2 divided by V naught, which comes as R T naught by twice V naught. And we have P1, which is our R T naught by V naught. This comes as our twice of P4. So we got the relationship between P1 and P4. Okay. And so let's come to the option A. It states that we have to find out the work done for the entire process. Okay. So we know we have isolated the process types for each, and let's find out for our work done. And work done for only, because we know that here we are going to have only two processes are there, isobaric and isochoric. Okay. So therefore the work done because of this isochoric will be equal to 0. So you can say work done due to this 2, 3 will be equal to 0, because the basic formula for work done is integration of pressure and the volume derivative. Okay, so means pressure difference basically. So it is isochoric, there is no pressure difference, so we are going to get this is equal to 0. And similarly for work done for 4, 1 will be also equal to 0. So therefore the work done will be only for 1, 2 process. 1 goes to 2 and 4 goes to 1. Okay. So we start with the first part, work done during 1 to 2, and we can say this as W12 will be our pressure, integration of our dV, and the limit starts from our V0 twice V0, and pressure we already know is our R T0 upon V0, and this comes as our twice V0 minus V0. V0 cancels out, and this comes as our R times T0. Okay, and for isochoric we already know it will be 0, and we will left with only 4, 1 will be also 0. We are left with only 3, 4, okay, which is isobaric. Therefore we can say for the process 3 to 4, so we can say W34 will be equal to our P, and this comes as our twice V naught d of V, and we get this as our R T naught upon twice V naught, and this is our V naught minus twice V naught, and we get this as minus of V naught cancels out, so this comes as minus R T naught by 2. Okay. Therefore, total work done that's our W will be equal to W from 1 2 plus W from 2 3 plus W from 3 4 plus W for 4 1. Okay. And for this 4 1 and 1 second, written correctly, yes, so for our 4 1 and 2 3 work done will be equal to 0. So this two terms will be 0, and rest we have already found out. So you can say W is equal to W12 is our RT naught minus RT naught divided by 2, which gives us 1 by 2 RT naught, and it means option A is correct. So this option A is correct. And B, it states that the above thermodynamic cycle exhibits only isochoric and adiabatic processes, but we found out that there is no adiabatic process. So option B is incorrect. Okay. So we can say option A is correct. And we can further write that process which we have are isobaric and isochoric. Okay. That means no adiabatic. Therefore, option B is incorrect. B is incorrect. And next, C and D are with respect to the heat transfer. So let's find out the heat transfer for all the processes. Heat transfers. So first process is our 1 to 2, which is our isobaric, and we can say that our delta U for 1 2 will be equal to 3 by 2 R, that is change in temperature. So this comes as our 3 by 2 R T naught, and work done we already found out, and we know that its work done is equal to R T naught. Therefore, we can say that Q12 will be equal to, according to our thermodynamics first law, 1 2. So this comes as our 3 by 2 R naught plus R naught, and giving us 5 by 2 R T naught. Okay. And then we come to our 2 to 3, which was our isochoric. And same process, we can say delta U from 2 3 will be equal to 3 by 2 R. This is T naught minus twice T naught, giving us minus 3 by 2 R T naught. Work done we already found out. For 2, 3, work done is our 0. Therefore, we can say this our energy will be only equal to our minus 3 by 2 R T naught, or because in the question it is only with respect to the magnitude, so we can say 2, 3 will be equal to 3 by 2 R T naught. Now we come to our 3, 4, and 3, 4 is our once again isobaric, and we can write delta U 3, 4 will be equal to 3 by 2 R T naught by 2 minus T naught, which gives us minus 3 by 4 R times T naught, and its work done we know is our minus R T naught by 2. Therefore, the heat for 3, 4 will be equal to, this will be our minus 3 by 4 R T naught minus R by 2, R T naught by 2, and its LCM will be over 4, and this will be over 2, this will be minus of 5 by 4 R T naught. And once again, considering the magnitude only, 3, 4 is equal to 5 by 4 R T naught. And finally, we have our 4, 1, which was our isochoric, and isochoric we can say our internal energy for 4, 1 will be equal to 3 by 2 R T naught minus T naught by 2, which gives us 3 by 4 R T naught, and its work done we know is 0. So for work done for 4, 1 is equal to 0. Therefore, the energy associated with 4, 1 will be equal to 3 by 4 R T naught. Now we come to the ratio which we are supposed to find out. So in the first we have to find out the ratio of 2 to 3 and 1 to 2, and for 2, 3 we are having 3 by 2 R T naught, and 1, 2 is 5 R T naught. So this comes as 3 by 2 R T naught and 5 by 2 R T naught. So here this R T naught, 2 and 2 cancels out, and this ratio comes as our 3 by 5. And we are supposed to find out next ratio is our 1 to 2 and 3 to 4, and 1 to 2 is our 5 by 2 R T naught, and 3 to 4 is our 5 by 4 R T naught. So in this case, this R T naught, 5 and 5 cancels out, and this comes as our 2. Okay. So therefore, option C is correct. Ratio is 5 by 3, and D is incorrect because ratio we found it is equal to 2. So C is correct and D is incorrect. So we can say that option C is correct, and we can say option D is wrong. Next question. It was asked in the year 2019 advance, and it states that a liquid at 30 degrees centigrade is poured very slowly into a calorimeter that is at a temperature of under 10 degrees centigrade. The boiling temperature of the liquid is 80 degrees centigrade. It is found that the first 5 grams of liquid completely evaporates. After pouring another 80 grams of liquid, the equilibrium temperature is found to be 50 degrees centigrade. The ratio of the latent heat of liquid to the specific heat will be. So basically, it is given that we have a boiling temperature of the liquid is 80 degrees centigrade, and we are pouring one second. Okay. And the calorimetric temperature is given as 110 degrees centigrade. Okay. So we have to remember that the boiling point of the liquid that is being poured inside the calorimeter is 80 degrees centigrade. And it says that only 5 grams of the liquid evaporates. It means when this 5 grams of the liquid is finished, when we are pouring it, the temperature of the calorimeter drops below 80 degrees centigrade. That's why it stops to evaporate. This is the basic thing. And when we add another 80 grams, the final equilibrium temperature is said to be 50 degrees centigrade. Okay, so we have to remember that. And so in this case, let us first of all, let me provide, you can say, the general derivation for this particular example, and then we can move forward. Okay. So in this case, let us assume that C is the specific heat of the liquid, specific heat of liquid, and capital L is our latent heat of vaporization of liquid, latent heat of vaporization of liquid, and capital C is heat capacity of calorimeter, heat capacity of calorimeter, and this small t is the initial temperature of poured liquid, initial temperature of poured liquid, and capital TB is the boiling temperature of liquid. Boiling temperature of liquid, and our TC0 is initial temperature of calorimeter, and let us assume that the mass of liquid that is being evaporated is our small n. So this small n is mass evaporated in first stage. And m is mass added in second stage. Added in second stage. And capital TF, this is final equilibrium temperature after second addition, that is second stage. Final equilibrium temperature after second addition. And in this case, all the temperature are in degree centigrade and mass are in gram as per the given question. So first of all, we know that the temperature of the calorimeter as liquid will be added to it, it is going to cool down. Okay. So the initial temperature of the calorimeter was our Tc0, and the final temperature of that will be our Tb0, sorry Tb. Okay, that is the boiling temperature of the liquid. So we can say that calorimeter cools from Tc0 to Tb. Okay. And during this cooling period, and we can say during this, n grams of liquid whose initial temperature was taken as T is heated to its boiling temperature, that was our Tb, and evaporates. So basically means the calorimeter temperature drops to the boiling point of our liquid, and the temperature of the liquid rises from its initial temperature to the boiling point, its boiling point, so that it evaporates. Therefore, we can use energy conservation. And this energy conservation, we can say that for our calorimeter, the energy lost will be equal to energy gained by the n gram of our liquid, that is Tb minus T and plus its latent heat, okay, because it is going to evaporate. And this was our first stage. So this process is our first stage. During this first stage, n gram was added and it evaporates. Now we come to our second stage. And in second stage, now the temperature of calorimeter is at Tb. So we can say at second stage, calorimeter, it is at temperature of Tb. Okay. And now we are adding additional m mass, but it is which is at a temperature of T, because it is same liquid. Okay. So initial temperature of liquid is always T. Okay. So we can say now addition of m gram of liquid at temperature T, and now the temperature of calorimeter as well as the liquid is further going to reduce to the final equilibrium temperature, which we have taken as TF. Therefore, we can say that final equilibrium temperature is TF. Obviously, this TF will be much below than our TB, so that the liquid does not evaporate. Okay, this is not mentioned, but we can just draw the conclusion. So once again, we are going to use energy conservation. And we can write that for our calorimeter, temperature is at TB, final temperature is TF, and then it is simple the cooling down of the liquid from the final temperature, and initial temperature was about T. And so from here we can find out this capital C will be equal to over MC TF minus T divided by TB minus TF. And from this equation, because we are supposed to find out the ratio, we are going to find from here this latent heat. Okay, so we can say that our L will be equal to, this will be capital C TC naught minus TB minus NC TB minus T, and this whole divided by N. Now we can easily find out the ratio, which is our ultimate final formula. So we can say our L upon one second. Okay, so this C which we found out here, we are going to substitute it here. Okay, then we are going to take C, small c as common. So therefore let me further write that our L will be equal to, and this we get will be equal to our MC TF minus T divided by TB minus TF multiplied by TC naught minus TB and divided by N, and this will be equal to minus small c, and this comes as TB minus T. Now we can take this small c common from both, that is going to give us final formula. L upon small c will be equal to, and this we can write as M TF minus small t TC naught minus TB and N times TB minus TF minus, and this comes as our TB minus T. So this is our final formula. Now we can just substitute the values. Okay. And we are given that further 80 grams added, and our TF is our final equilibrium temperature which is again 50. T is the initial temperature of the liquid, and that is given to us as 30 degree. Tc0 is our calorimeter initial temperature, which is our 110, and Tb is the boiling temperature, which is 80, and N is our initially, which we have put first stage, that is 50, and rest of things will be same, 80 minus 50 minus, and this comes as our 80 minus 30. Therefore, we get this ratio L upon C will be equal to, this will be our 20, and this will be our 30, and this will be also our 30. Okay, so this 30 and 30 goes away, and this goes by 5, goes by 4, so this will be our 320 minus 50. So we get this L upon small c will be equal to 270 degree centigrade, which was asked for, 270. Next question. It states that a mixture of ideal gas containing 5 moles of monoatomic gas and 1 mole of rigid diatomic gas is initially at pressure P0, volume V0, and temperature T0. If the gas mixture is adiabatically compressed to a volume V0 by 4, then the correct statements are this 2 and 3 raised power values are given to us, which we can use during the further process. So first thing, we have to find out the work done, and okay, so here easiest part will be first of all find out the adiabatic constant, that is our gamma, okay, because that is for our mixture. So let us start with our adiabatic constant, and we know that it is so here we have to find out the adiabatic constant for the mixture. So we can say our gamma for our mixture will be equal to C of P for our mixture and C of V for our mixture, and we know that our C of V for our mixture will be equal to our first C of V plus for our second C of for the second, and first plus second, okay, means number of moles, and we substitute the value, we get this as our, this will be our 5, and first one is our 5 moles monoatomic, so that comes as 3 by 2 R, plus second one is 1 mole and is our diatomic, so that will be 5 by 2 R, and this will be 5 plus 1, so this will be equal to our 15 plus 5, that will be 20, and 2 is going to give us 10, so 10 by 6 R, or we can say 5 by 3 R, and we can simply write that for our C of P for our mix will be equal to CV for our C of V for mix plus R. So we get this as 5 by 3R plus R, giving us 8 by 3 times R, which now comes quite easy. So we get our mixture is equal to, we get this as C of P, that is 8 by 3, and this comes as our 5 upon 3 R. And here this R 3 cancels out, so this will be equal to our 8 by 5, giving us 1.6. So option D is correct. And so let's find out the work done, that is during the process is 13 R T naught. Okay. So we have to find out, first of all, the process is our adiabatic. We have an adiabatic process, and we know that for this our Q is equal to 0. Therefore, from first law, we can write that our delta U will be equal to work done on the gas, because Q is equal to 0. And we can write it that work done on the gas will be equal to delta U in terms of the temperature. We can write this as N C of V for our mixture and final temperature minus initial temperature. So this adiabatic is a process, therefore we can use its standard relationship. So we can say our TV so for adiabatic process, TV gamma minus 1, and this we know is our constant, and therefore we can write this as our T final V final gamma minus 1 will be equal to, if we say initial is our T naught, V naught gamma minus 1. Therefore we can say our TF will be equal to, this is our T naught, V naught and V final gamma minus 1. And it says that it is compressed up to 1/4 of the volume. Therefore we can write that our T final will be equal to our T naught 4 gamma minus 1, and this gamma minus 1 is our 0.6. So we can say this will be our T naught 4 raised to power 0.6. And we can write this as our, so we can say that our TF will be equal to 2.2 times T naught. And So we get this work done. Let us take only the magnitude will be equal to delta of U, and that will be equal to, we have our n CV mix. CV mix is our (5R/3), and total moles have a 6. So we get this as 6 multiplied by 5/3 times R, and we have a final temperature is 2.2 T naught minus T naught, and 6 goes by 2, so this comes as 10 R, and it will be equal to 1.2, so that will be our (1.210), so that we can say is approximately equal to 13 R T naught. Therefore, option A is correct. A is correct. Next is our average kinetic energy of the gas mixture after compression lies between 18 R T naught and 19 R T naught. And so we are interested now in our average kinetic energy, and we know that our internal energy of a mixture after compression equals to the total kinetic energy of the ideal gases with respect to their degree of freedom. We can just interpret it something like this. Okay, so we can say the internal energy of the mixture after compression equals total. Total basically means translational plus rotational. Kinetic energy for ideal gas with those degree of freedom. Degree of freedom. Thus, we can say that total internal energy that is our U of F will be equal to N, and we have this as our C of V mixture and T of F. So we already know these values, we substitute them, we get this as our U of F, number of moles is our 6, and this is our 5/3 R, and this is our TF in terms of T naught is our 2.2 T naught. This goes by 2, so this will equal to 10 R and giving us approximately 22 R T naught. But in the question it is asked that it lies between 18 and 19, so option B is incorrect. Is incorrect. And now we come to option C. The final pressure of the gas mixture after compression is in between 9 P naught and 10 P naught. Okay. So we are interested in finding out their pressure, final pressure. Yes, final pressure of the mixture. So we can say, because it is adiabatic process, so we can write for adiabatic process, we know that our PV raised to power gamma is equal to constant. Okay. Therefore, we can write this as our PF VF gamma is equal to P naught V naught gamma, giving us the final pressure is equal to our P naught V naught and our VF raised to power gamma. So we get this as P naught 4 raised to power gamma, and this comes as our P naught 4 raised to power 1.6, and this we can say that our final pressure PF is approximately equal to 9.19 times P naught, and it was says it is in between 9 and 10, so option C is correct. C is correct. Next question. Okay, so it is a multi-part question. It was asked in the year 2019 advance, and it states that in a thermodynamic process on an ideal monatomic gas, the infinitesimal heat absorbed by the gas mixture is given as T times delta X, where T is the temperature of the system and delta X is infinitesimal change in the thermodynamic quantity X of the system. For a mole of monatomic ideal gas X given by the equation, here R is the gas constant, V is the volume of the gas, TA and VA are constant. And it says that the list 1 below gives some quantity involved in the process and list 2 gives some possible values of these quantities. So we are having list 1 and this 2. So list 1 is basically the work done, internal energy, heat absorbed during the various processes, and these are its values. Okay. And so based on this we are having two parts. This is part A. If the process carried out on 1 mole of monatomic ideal gas is as shown in the figure in the PV diagram, P naught V naught is equal to 1 R T naught divided by 3, the correct match is. So basic process is given to us. So in this PV diagram, we are having the process which starts from 1 goes to 2 and then goes to 3. So from 1 to 2 we are having pressure constant, that is it is isobaric, and from 2 to 3 volume is constant, that is it is isochoric. Okay. So we can just write it out. So for 1, we are having V0, P0, and for 2, we have twice V0 and P0, and for 3, we are having twice V0 and thrice P0 by 2. And also process from 1 to 2 is isobaric, and from 2 to 3 is our isochoric. And we are given that P0 V0 is equal to 1 by 3 R times T0. So we are also given that P0 V0 is equal to 1 by 3 R times T0. Okay. So let's find out what will be the temperature of all these states, T1, T2 and T3. You can say temperature for 3 states. Temperature at 3 states. So first we have a T1, which will be equal to our P0 V0 upon R, and which will be equal to obviously 1 by 3 T0. Then we have our T2. T2 will be our P0, volume is our twice V0 and divided by R, which gives us 2 by 3 times T0. And finally we are having our T3. We are having our T3, and which gives us 3 by 2 P0 and twice V0 divided by R, and this gives us 3 P0 V0 upon R, which is equal to our T0. Yes. Okay. So because we have to find out the work done and all the processes, so let us try it one by one. So we start with the work done by the process in 1, 2 and 3. So we have our work done by system in process 1 to 2 and 2 to 3. And so this work done in 1 to 3 will be equal to work done from 1 to 2 plus work done from 2 to 3. But for our 2 to 3, the volume is our constant, so this work done will be 0. So we get this will be equal to work done from 1 to 2, and that will be equal to P0 and the difference in their volume, which gives us P0 twice V0 and minus V0. Okay, and from here we get that our 1, 2, 3 will be equal to P0 V0, but it is given that P0 V0 is equal to 1 by 3 R times T0. Okay, so we get the work done during 1 to 3 is our 1 by 3 R T0. So our 1 is matched with our Q. Therefore, from here we can say that our 1 belongs to Q. Now second is our change in internal energy during the same process. Change in internal energy for 1, 2 and 3. Okay. And we are given as 1 mole. Therefore, we can write directly delta U is equal to 3 by 2 times R. Basically, it is NC of V, and same formula, difference in temperature, T3 minus T1. Okay. And this gives us a 3 by 2R, and we have this as our T0 minus 1 by 3 T0. This gives us 3 by 2R multiplied by 2 by 3 T0. Therefore, this change in energy is equal to this 2, 2, 3 and 3 cancels out, comes as R T0. So we have change in energy, that is option 2 is R T0, so it matches with our R. Second goes to R. Next is our heat absorbed by the system for same process 1, 2, 3. Heat absorbed by system in 1 to 2, 2 to 3. And according to first law, we have heat given, internal energy change and work done. Therefore, we can write that our internal heat 1 to 3 is equal to our change internally 1 to 3 plus work done 1 to 3. We simply substitute the values. Q1 to 3 is equal to, and this comes as our RT0 plus 1 by 3 RT0, and this comes as 4 by 3 RT0. Okay. So we get this as 1 by 3, 4 by 3. So we get this second goes to S. Third goes to S. Therefore, we can say our third goes to S. And finally, in this part, we have to find out heat absorbed in the process 1 to 2. So we have heat absorbed in the process 1 to 2. So only 1 to 2 is required. So we can say delta 2, 1, 2 is equal to 3 by 2 R and their temperature difference. So we get this as 3 by 2 R, and this is about 2 by 3 T0 minus T0. Sorry, minus 3 0. temperature is 2 by 3 and 1 by 3, so it is 1 by 3, and this gives us 1 by 3, and 3 cancels out, so we get this as 1 by 2 or T naught. And now we find out the work done. Work done for 1 by 2 is our P naught V naught, which is our 1 by 3 or T naught. Therefore, heat absorbed to process 1 2 is equal to internal energy plus work done, which comes as 1 by 2 R T naught plus 1 by 3 R T naught, giving us 5 by 6 R T naught. So therefore, we get from here this force matches with our U. 5 by 6, so fourth goes to U. So we have this as fourth matches with U. Okay. And so we had one with Q, so one with Q, and second with R, third with S. Option A is correct. A is correct. Next question, it is based on the same, but here the process is given as in the form of TV, okay, TV diagram. So it states that if the process carried out on 1 mole of monoatomic gas is as shown in figure, and the TV diagram, and P naught V naught is equal to 1 by 3 R T naught, the correct match will be. Okay, now we have to do it for same, but for because it is 1 to 2 is now isothermal, and 2 to 3 is still our isocoric. Volume is constant. Okay. So now in this case, basically we can mark the points as temperature, volume. Therefore, we have our first part, that is our temperature is T naught by 3 and volume is V naught. We have our second point, temperature is still T naught by 3 and volume is given as twice V naught. And we have our third point, which gives us that temperature is T naught and volume is twice V naught. Now we can mark the processes. So we can say from 1 to 2 we are having this isothermal, and from 2 to 3 we are having is isocoric. Okay. And same things, but we have for this different based on the graph which is given at temperature and volume. So we start with first is work done, and so for the work done, that is work done in the process 1 to 3 will be equal to work done between 1 and 2 and work done between 2 and 3. 2 and 3 is our isocoric, so this work done will be 0. This will equal to work done because of 1 to 2. And the process is our isothermal. Therefore, we can write this as of nR T1 natural log of V2 by V1, and number of moles are given to as 1. So therefore we can write that work done 1, 2, 3 will be equal to 1R, and T1 is our T0 by 3, and the volume is our twice V0 by V0. This V0 and V0 goes away, so this comes as our R T0 by 3 and natural log of 2. Okay, so we can check it out. Here it comes as our, okay, it matches none of the options. Sorry, it is 1 by 3. This is 1 by 3. So therefore second case we can say that 1 matches with our P. So this matches with our 1. So we can say 1 goes to P. Okay. So we can say our 1 goes to P. Next is our internal energy change. Same process, that is our delta U for 1 to 3. It will be N C of V, temperature at their difference, and this comes as our 3 by 2 times R, and we have our T0 minus T0 by 3, and from here we get this U1 to 3 will be equal to our, this will be coming as 2 by 3, 2 by 3 and 3 by 2 cancels out, so it will be our R T0. Okay. And matching I'll do later on, okay, because then we come to our next, that the heat absorbed Q1 to 3, and Q1 to 3 will be our delta U 1 to 3 plus work done 1 to 3. So we have this as our RT0, and for 1 to 3 is our RT0 divided by 3 natural log of 2. So we can take, so Q1 to 3 will be equal to our RT0, we can take as common. Let us talk this as 3. So this comes as our 3 plus natural log of 2. And finally we are having our heat absorbed, that is Q from 1 to 2, and that is our isothermal process. So this we can say is simply our work done between 1 to 2, which comes as our R T0 by 3 natural log of 2. Okay. So let me match the options now. Okay, so change in internal energy, that was our Q1 to 3, we get this as our R T0. So this second R matches with our second, and heat absorbed in 1 to 3 was our natural log, and so it comes as our, this T matches with our third, And finally we are having heat absorbed from 1 to 2, and heat absorbed 1 to 2 is simply our work done, which is our R. So this, okay, so it matches also with our, one second, I think, heat absorbed in the system from 1 to 2, and it is our RT naught divided by 3 natural log of 2. So this also matches with 4. Oh. So we have our P matches with 4, so this goes with our P, and this third matches with our T, this matches with our T, and second internal energy, and second matches with R, and our first matches with work done in the process is first matches with first, matches with P. So this is our PRTP. Okay, so we have to check PRTP. So we have PRTP. So we have first PRTP, option C is correct. Option C is correct. So this completes all the 5 questions. 2018 1 question, 2019 4 questions. So all these questions were from the advance for 2018 as well as 2019. Thank you.